It's amazing to think about how much sharper the world's become, visually, through all the advances in technology.
Yeah, that's
Like,
great.
from the detail you see in those medical scans
Uh-huh.
to, like, the crazy precision of satellite imagery.
Right.
It seems like we're constantly pushing the limits of how much detail we can capture and actually see.
Absolutely. And it's not just about having like prettier pictures.
Right.
This high resolution visual perception is more and more important for so many everyday tasks.
Yeah, totally.
Like just navigating with digital maps or interacting with all these complex software interfaces.
Yeah, you really need that high resolution.
Exactly.
So that brings us to our deep dive today.
Yeah, today we're diving into something pretty groundbreaking, I think. It's called pre-training with scale-selective scaling.
Okay.
PS3 for short. And PS3 is a big deal because it lets us pre-train these vision models at 4K resolution,
4K, wow.
which is something a lot of people have been trying to achieve for a while now,
Yeah.
but it's been really difficult.
Yeah, I can imagine.
And the big thing here, the core insight, is the idea of scale selective processing. And this is actually one of the really revolutionary aspects of this from an academic perspective.
Okay.
This idea is what allows PS3 to achieve something that seemed kind of impossible before.
Hmm.
Pre-training these vision models at this stunning 4K resolution, but with almost the same computational cost as we see with today's low-res models.
So 4K pre-training with basically the same cost.
Yeah, pretty much.
That's a huge leap.
It is.
Because, I mean, think about current models, right?
Right.
Like CLIP and SIGLIP. They typically work at much lower resolutions.
Yeah, they top out around 378 by 378 pixels, I think.
Yeah, so why haven't we been able to do this before?
So the main challenge has always been just how computationally expensive it is.
Okay.
When you're dealing with images that have way more pixels, you need way more computing power to handle them,
Yeah, makes sense.
especially for vision transformers, which are like the dominant architecture in this field right now.
Uh-huh.
The costs can actually increase by a power of 4 as the resolution goes up.
Wow.
So like if you tried to pre-train something like SIGLIP directly at 4K
Yeah.
using the usual global contrastive learning methods,
Uh-huh.
you'd need a ridiculous amount of resources.
So basically, it would be impossible.
Pretty much, yeah.
Okay, so for everyone listening, our mission for this deep dive is to really grasp the brilliance behind PS3,
Yeah.
both in a practical sense and academically too. Like, how does it manage to dodge this huge computational roadblock?
Exactly.
What's so new and innovative about its data, its model, and its training algorithms that allows it to actually do 4K pre-training?
Right.
The sources you gave me really get into the specifics of each of these areas.
They do, and it all starts with that central innovation, scale selective processing.
Okay, so let's break down this scale selective processing a bit more.
Sure.
What's the technical side of it look like?
Basically, the key insight is that to learn detailed features from a high-resolution image,
Yeah.
a model doesn't actually need to process the entire image at that, crazy high level of detail all at once.
Hmm.
Instead, it can kind of focus on contrasting these local high-res regions
Okay.
with equally detailed, local captions.
Here.
Remember that stop sign example from the paper?
Yeah, I do.
To understand the text stop,
Uh-huh.
our own eyes, our own visual system doesn't, look at the whole scene in ultra high definition all at once.
Right?
Our attention goes to the sign.
Yeah.
And even more specifically to like the shapes of the letters themselves.
Uh-huh.
And PS3 tries to recreate that kind of efficiency in a vision model.
So it's like it's still forcing the model to process every single pixel of a massive 4K image.
Right.
To understand something small and detailed, it just directs its high-resolution power to the parts that actually matter.
Exactly.
And that translates into those big cost savings, right?
Yeah, exactly. By focusing its high-res computations only on these selected regions,
Okay.
PS3 manages to keep the computational cost pretty much constant,
Hmm.
even when it's scaling up to 4K.
Wow.
The research actually shows a 79x reduction in the computation needed for pre-training.
79 times.
Yeah, 79 times less than if you were using global contrastive learning like SIGLIP across that whole 4K image.
That is mind-blowing.
It's a big change.
A 79-fold decrease. That's a whole different way of thinking about it.
It is.
And it seems like the big academic contribution here.
Yeah.
is this really elegant way of separating the resolution of a region being processed from the total resolution of the image itself.
Exactly. It's about being scared selective, using that fine-grained processing only where it's absolutely needed,
Hmm.
without the crazy computational burden of analyzing the whole image at high resolution.
So it sounds like to make this actually work,
Uh-huh.
there had to be innovation on multiple levels, right?
Oh, absolutely.
You can't just tell a model to see tiny details if it hasn't been trained on data with those details in the first place.
Exactly. And most of the image text data sets out there are, lower resolution.
Right.
They just don't have the level of detail you'd need to effectively train a model at 4K.
Okay.
So to fix this, the researchers put together a whole new data set.
Okay.
Massive, 75 million high-resolution images from 1K to 4K resolution.
Wow.
38 million of those were natural images, like from datasets like Datacomp and SA1B.
Okay.
And the other 37 million were document images.
Document images.
Yeah, from collections like IDL and PDFA.
Okay.
So we're talking a lot of images.
75 million high-res images is a lot to process.
It is.
But then there's the challenge of actually providing the model with good labels.
Right.
Right, those detailed local captions and the bounding boxes
Yeah.
to tell it where those important regions are in the high-res image.
Exactly. And creating those annotations manually at that scale would be a crazy amount of work.
Yeah, for
So
sure.
this is where their automated pipeline comes in.
Okay, so what do they do?
So for actual images, the first step was to figure out which parts of the image were visually important.
Okay.
So they used a model called efficient VSAM for saliency detection.
Saliency detection.
Oh.
So what does that actually do?
Basically, it highlights all the different objects and areas in an image.
So it's kind of like it's trying to figure out what are the interesting parts of this picture.
Exactly. And then they used a really clever strategy to select which regions to actually focus on.
Okay.
They looked at the segmentation masks, the ones that the saliency model produced,
Uh-huh.
and they focused on regions with either like very small masks,
Okay.
suggesting, a tiny detailed object,
Hmm.
or regions with super dense masks, meaning there's like a complex area with lots of fine components.
Right.
The idea being that those areas probably have the most detail for the high-res pre-training.
Yeah, that makes sense. I mean, a patch of plain sky probably doesn't have the same level of detail as like a close-up of some intricate pattern
Exactly.
or some fine text or something like that.
Exactly.
Okay.
Once they had those important regions, they used a powerful multi-modal large language model, or an MLLM,
Okay.
like Qwen2-VL, for example,
Yeah.
to create descriptions for them.
But they didn't just show the MLLM those little cropped out regions, right?
No, that's important.
Okay.
They also gave it the entire original high-res image,
Okay.
so it had that global context.
Hmm.
This way, the MLLM could generate a more accurate and relevant caption that specifically describes what's in that local crop.
Got it.
And through this whole process, they created like 3 or 4 local caption and bounding box pairs for each natural image,
Okay.
ending up with a total of 134 million pairs.
134 million?
Yeah, with an average bounding box size of around 400 by 400 pixels.
So that's a huge amount of localized high-resolution training data.
It is, and it was all done automatically.
Wow, very cool.
And then for the document images, they used the existing annotations in the IDL and PDFA datasets.
Oh, smart.
Yeah, those datasets already had detailed bounding box information and OCR results for things like sentences and words.
Right, makes sense.
So they could just directly use that text as the local captions.
Okay.
And that gave them another 148 million training pairs
Wow.
with a smaller average bounding box size, like around 50 by 400 pixels.
Okay.
Which makes sense considering the shape of lines of text.
Yeah, that makes sense.
And so for natural images, they did create global captions using that same MLM process.
Uh-huh.
But for document images, they decided not to use global captions.
Hmm.
Really, the takeaway here is that they created this huge data set of high-res localized image text pairs,
Yeah.
which was a crucial step for their 4K pre-training approach.
Absolutely. Okay, so they've addressed this need for high-res training data
Uh-huh.
in a very new way. Now, let's get into the actual PS3 model itself.
Okay.
How is it built to do this scale selective processing?
So the PS3 model has this 3-stage architecture that's really key to its scale selective processing ability.
Okay.
The first stage extracts low-resolution global features from the image.
Okay.
And for this, they actually use the same vision transformer architecture, the VIOT,
Uh-huh.
that's in the SIGLIP OSO 400M model.
Okay.
This stage processes the input image at a relatively low res, 378 pixels,
Okay.
and it produces this 27 by 27 grid of feature tokens.
So it's kind of getting a general overview of the image.
Exactly.
At a resolution that's, easier to manage computationally.
Right, at a manageable level.
What happens in that second stage, the crucial one?
So stage 2 is where the scale selective magic happens,
Okay.
through a process of picking out the important regions in the image.
Got it.
And this selection can happen in two ways.
Okay.
Top-down, guided by a texaquant, if there is one,
Uh-huh.
or bottom-up, based on just how visually interesting different regions of the image are, like we talked about before.
So if you ask the model a question about a specific object,
Yeah,
it would use top-down selection to zoom in on that area mentioned in the question.
exactly.
And if it's just looking at an image, no specific question,
Uh-huh.
it would use bottom-up saliency to find the visually interesting spots.
Exactly.
Okay.
In this stage, the model predicts a selection score for each spot in the low-res feature map from stage 1.
Okay.
And this score tells you how important that region is. For top-down, this score is based on how similar the low-res features at that spot are to the embedding of the input text prompt.
Okay.
And for bottom-up, it's based on similarity to a learnable vector that the model learns to associate with those intrinsically salient regions.
Got it.
But there's a bit of a catch.
Okay.
We talked about how important fine-grained localization is for understanding high-res images.
Right.
So how can these low-res features from stage 1 actually pinpoint those details well enough for the high-res processing in the next stage?
Yeah, that's a great question.
That's a great point.
So what do they do?
So they had to get creative.
Okay.
To overcome this limitation of low-res features, they also use additional high-res features,
Okay.
extracted by a lightweight convex encoder. This encoder works on the image at a much higher resolution,
Okay.
1512 by 1512 pixels.
Wow.
And then the selection scores from both the low-res features, for semantic relevance,
Uh-huh.
and the high-res features for the spatial detail
Okay.
are interpolated to the same size and then averaged together.
Okay.
This fusion lets the model use both the global understanding from the low-res branch
Yeah.
and the detailed spatial info from the high-res branch.
So it's combining different levels of information to be more precise in selecting these patches.
Exactly, leading to much more accurate region selection.
Very cool.
And then in stage 3, this is where the high-resolution details of those selected regions are processed.
Okay, so what happens there?
So first, they take the original high-res image
Uh-huh.
and resize it to several different scales, like
Okay.
756 by 756, 1512 by 1512.
Hmm.
And even up to 3780 by 3780 for that full 4K resolution.
So the same region of the image is now represented at different levels of detail all at the same time.
Exactly.
Oh, wow.
And then for each of these scales,
Uh-huh.
the model selects the top K patches
Okay.
based on those selection scores from stage 2.
Got it.
And during pre-training, the number of patches they select at each scale is proportional to the total number available at that scale.
Okay.
So the model is looking at the same region of the image, but at all these different resolutions.
Got it. So they have all these high-resolution patches chosen based on their importance, all these different scales.
Yeah.
How does the model actually learn from them?
So after they embed each of these patches, they add positional embeddings.
Okay.
And this includes modified versions of those low-res positional embeddings, specifically mapped to where the high-res patch is in the original image.
Okay.
But they also add this new thing, a scale-aware positional embedding.
Okay, so what is that?
Think of it like a unique ID tag that lets the vision transformer tell the difference between tokens that came from different scales of the same region, so it knows how detailed each token is.
Right, right.
And to maintain that global context from stage 1.
Yeah, that's really important.
And they use the key and value cache, the KV cache, generated from those low-res tokens in stage 1.
Uh-huh.
So this cache, it's like a summary of the whole scene,
Okay.
and they add it to the self-attention layers in stage 3.
So the model can see the bigger picture.
Exactly, even while it's focusing on those tiny details in the high-res regions.
Wow, that's really clever.
So this whole system of multi-scale processing with that global and local context fusion,
Yeah.
that's a big part of what makes the PS3 architecture so innovative.
It's a very sophisticated way to deal with all that information at different scales.
It is.
Now, let's talk about the third piece of the puzzle, the pre-training algorithm.
Okay.
How do they actually train this model with all this new data and this unique architecture?
So the PS3 algorithm uses a joint pre-training strategy.
Okay.
with two main goals. First, to learn good high-res visual representations
Okay.
by connecting visual features with text descriptions.
Right.
Second, to train those top-down and bottom-up patch selection mechanisms we talked about,
Okay.
so it can find the most useful regions.
So how do they actually learn those high-resolution visual representations?
They use what's called a localized contrastive loss.
Okay.
Basically, they try to bring the feature vectors from those selected high-res regions
Yeah.
closer to the feature vectors of their matching local captions in this embedding space,
Okay.
while pushing them further away from unrelated captions. And they use a sigmoid contrastive loss function.
Okay.
It's similar to the one used in iglip.
Uh-huh.
And to make training faster and more stable, they actually start with the vision transformer backbone and the text encoder,
Okay.
initialized with weights that have been pre-trained on Siglet.
So they're using that existing knowledge to jumpstart the learning.
Exactly.
Right.
And they've got a few key design choices in this contrastive pre-training that
Right.
really help make it work and are pretty novel, academically speaking.
What are some of the big ones?
One of the biggest is that during pre-training, they don't just use the model's predictions for selecting the patches.
Okay.
They also use ground truth scores, the ones derived from those bounding box annotations in their high-res data set.
Okay.
It's kind of like teacher forcing for those who are familiar with that from training recurrent neural networks. By guiding the initial learning this way,
Yeah.
they help the model learn to select patches more accurately and reliably. Another important choice is how they handle the feature tokens from those high-res patches.
Okay.
When they pool them together to get one feature vector for the contrastive learning,
Uh-huh.
they only use tokens that are actually inside the ground truth bounding boxes.
Okay. This makes sure the model doesn't accidentally link up irrelevant visual features from outside the important region with the local caption.
So it's a very focused way of teaching it the right associations.
Exactly.
And what other algorithmic innovations are they using?
Another one is mixing global and local contrastive learning in each training batch. Okay.
So each batch has pairs of, high-res region features and their local captions,
Uh-huh.
but also pairs of low-res global image features and their global captions.
Okay.
This mixing helps the model keep its overall understanding of the scene while still learning those fine details.
Right. Doesn't get too lost in the weeds.
Exactly. And the last big one is they avoid something called intra-image contrast.
Okay, what is that?
Well, since one high-res image can have multiple important regions with their own local captions,
Yeah.
they make sure that each image only shows up once in a given training batch.
Okay.
This prevents the model from learning to tell the difference between regions in the same image just because they look kind of similar, which could actually mess up the learning of more general features.
So all of these are really careful and academically important design choices that help this localized contrastive learning approach work so well.
They are.
Okay, so now we've got the data, the model, the training algorithm.
Right.
How does it actually perform in the real world?
So to test PS3, they ran experiments on a bunch of different resolution-sensitive benchmark datasets.
Okay.
Like TextVQA, ChartQA, DocVQA, InfoVQA, and others.
Wow, that's a lot.
Yeah.
And they even created a new benchmark, right?
They did, because they realized that a lot of existing benchmarks,
Yeah.
even the ones at 4K images, they don't actually require the model to use that full 4K resolution
Oh, that's interesting.
to answer the questions correctly.
Okay.
So they made a new one called 4K Pro,
Okay.
and it's specifically designed to test a model's ability to really understand those fine details you only see at 4K resolution. In realistic situations like, self-driving cars, household tasks, understanding game interfaces,
Right.
things like that.
So the questions in 4K Pro are designed in a way that you can't answer them accurately,
Exactly.
unless you can actually see those details.
You need that 4K perception.
That's a really cool idea.
It is.
And what were the results?
One of the biggest findings was that pre-training with PS3 really helps these MLLMs do much better on tasks that need high resolution compared to models that weren't trained this way.
Okay.
And from an academic standpoint, what's really impressive is that these improvements come with a pretty much constant pre-training cost, even when scaling up to 4K.
Wow.
So for example, they found that processing the same number of high-res tokens, but at a higher resolution, like 1512, gave better accuracy than processing them at a lower resolution, like 756.
Okay.
So higher input resolution is better if your computational budget for that high-res stage is fixed.
That's a pretty big deal.
It is.
Traditional methods really struggle to scale to 4K.
Yeah, they hit those computational bottlenecks.
Right, right.
But PS3 gets to 4K with similar costs to much lower resolutions.
Hmm.
And that leads to better performance, especially on benchmarks like VBench, which is designed to test high-res understanding.
This near constant cost scaling really is a game changer.
It was.
What about their new benchmark, the 4K Pro?
This is where PS3 really shines.
Okay.
They found that a lot of benchmarks don't actually need true 4K perception.
Hmm.
But on 4K Pro, their model, VILA-HD, pre-trained with PS3 at 4K resolution, blew away even state-of-the-art MLLMs.
Really?
Yeah, even models like GPT-4o and Qwen2-VL,
Wow.
both in terms of accuracy and efficiency.
So it's really showing that pre-training at 4K is crucial for tasks that need that fine detail.
Absolutely.
And creating 4K Pro itself is a big academic contribution.
It is.
It's pushing the boundaries of how we evaluate these models.
Exactly.
And how did PS3 stack up against other methods that try to improve efficiency in vision models,
Uh-huh.
like those token pruning techniques?
So they found that PS3's learned patch selection was more efficient in terms of like how fast the vision transformer runs.
Okay.
And it either did better than or about the same as existing token pruning methods. But the big thing is PS3 is the only one that can actually handle 4K images.
Oh, okay.
Those other token pruning methods, they struggle at that resolution.
Right.
So it shows that PS3's selective processing is better suited for high-res situations.
Then these more general ways of reducing tokens.
Exactly.
And was it just limited to one type of vision encoder?
No, they actually showed that PS3 can work with different foundational vision models.
Okay.
They tested it with SIGLIP and C-Radio V2L.
Uh-huh.
And in both cases, pre-training with PS3 led to big improvements
Hmm.
beyond what those models could do originally.
Okay.
And it also outperformed other scaling methods like AnyRes and S applied to those same models.
So PS3 is a general technique that can help different vision encoders see better at high resolution.
Exactly.
And the paper also had those ablation studies
Right.
where they looked at the impact of each part of the PS3 system.
Yeah, they really dug into the specifics.
What were some of the key findings from those?
So they found that contrasting features within those ground truth boxes during training was really important,
Okay.
and that avoiding contrast between different parts of the same image was also beneficial.
Makes sense.
For the model architecture, they found that including that low-res KV cache in stage 3 was a big deal.
Right, to provide that global context to the high-res features.
Yeah, it made a big difference in performance.
Hmm.
And they showed that using multiple scales for feature extraction was better than just relying on the highest resolution alone.
Okay.
And their analysis also showed that those learned patch selection mechanisms,
Mm-hmm.
both the top-down and bottom-up versions,
Yeah.
they help the model focus on the most relevant information,
Okay.
leading to better accuracy and faster training compared to picking patches randomly.
So all of these results give really valuable guidance for future research in this area.
They do.
Did they find one optimal balance for processing at different image scales?
So, interestingly, the best balance of patch selection across the different scales actually depends on the specific task. For instance, if you need to understand the whole scene, even if it's at a lower level of detail,
Uh-huh.
you might want to pick more patches at lower resolutions.
Okay.
But if you need super fine-grained understanding of a small area,
Yeah.
you'd probably want more patches at those higher resolutions.
So different tasks need different approaches.
Exactly.
It shows that multi-scale processing is complex
It is.
and that models could be adapted to focus on certain scales based on what they need to do.
Right.
And the data used for fine-tuning downstream tasks was important too, right?
Yes, they found that even simple methods of creating high-res fine-tuning data can help.
Okay.
It helps align those high-res features from PS3 pre-training
Uh-huh.
with the language model's understanding of text,
Got it.
which leads to better performance on tasks that are sensitive to resolution.
So it's not just about the pre-training data, but the fine-tuning data as well.
Exactly.
And lastly, they had some visualizations of those learned features.
Yeah, those were really interesting.
What does those show?
They showed that PS3 lets the model learn much sharper and more detailed visual features at 4K resolution,
Okay.
compared to those baseline methods like S2 and AnyRes,
Uh-huh.
which often produce kind of blurry or noisy representations.
So PS3 is a big step forward.
Oh, hey, I think our listeners got something to say.
Oh, hi there. No, we weren't stopping at all.
Thanks for checking in. We're just getting to the really fascinating conclusions.
Exactly. So, as we were saying, PS3 seems to be a really significant leap forward.
Yeah, showing us much clearer visual features at that incredible 4K resolution.
And this isn't just about making things look nicer.
Right, it has real implications for how these models understand the world.
Absolutely. Think back to that stop sign example.
Yeah.
Being able to clearly see and interpret those fine details is crucial in so many situations.
Like autonomous driving, which the paper actually touches on.
It does. That ability to spot even small details at a distance.
Right, it could be a matter of safety.
Exactly. And it's not just limited to that.
No, we also saw examples in household tasks.
Like identifying objects or reading text on labels,
And even in things like understanding user interfaces.
where tiny icons or fine print can be really important.
So this ability to process 4K resolution efficiently.
It really opens up a whole new level of visual understanding for these AI systems.
It does. And the fact that they achieved this with a near constant pre-training cost.
That's what makes it so revolutionary from an academic perspective.
Yeah, it breaks down those previous computational barriers.
Allowing us to train models that can truly see the world in high definition.
So what does this all mean for the future?
Well, it suggests we can move beyond those lower resolution limitations
Yeah.
and build MLLMs that have a much richer and more detailed perception.
Which could lead to all sorts of exciting applications we haven't even thought of yet.
Absolutely. This feels like a real step towards more intelligent and capable AI systems.
It's been a fascinating journey unpacking all of this.
Definitely. And thanks so much for tuning in and keeping us on track.
We really appreciate you joining us for this deep dive. Until next time.
Goodbye for now.